a pleasure to introduce our first speaker, Kenji Fukaya, who has a new title, but I think a similar content. Please.
Thank you very much, and thank you for organizers giving me the opportunity to talk here. And the title is quotation Hodge Theory, quotation from Floer homology. And here it is. Yeah. So one definition is O means three of my collaborators, Yongin O, Hiroshi Ohta, and Kaoru Ono. So I think that in this conference there is practically not so many people working on symplectic geometry, which is now I'm working on. So I want to review something which maybe many of you, most of you know already very well. It's a Hodge theory. So it's a very classical topics in complex geometry, but it's a bit different way I want to explain. So you consider Kähler manifold, and you consider differential forms of type P and Q, P in dzi and Q in dzi bar. Then in the Hodge theory, you have two differential operators, round D operators, round D bar operators. And you have this, the first one lays 1 on this P part, and the second one lays 1 for Q part. And we consider this D bar plus U D. U is a formal parameter, so I think that you know very well that we have an equality. D bar square is D square is 0, and D bar D plus DD bar is 0. So you have, using this very famous and classical equalities, this guy is a boundary operator. So you have you can cook up homology group. And this is a kind of idea that if when you use a parameter, so when U is 0, you have a D bar cohomology. And when U is infinity, you have a D cohomology. And when U is 1, you have a usual drum. So you have a kind of one parameter family of differential operators. And if you calculate cohomology of this guy, then it is a very trivial thing. It's a usual cohomology tensor with this formal parameter. And the reason is a very important equality here, right? I mean, Laplace operator of drum operator is equal to Laplace operator of round D and Laplace operator of D bar. So it kind of, these three basically give the same cohomology, and you have this. So this is a reflection of this basic fact in Hodge theory. And you can integrate differential forms, or these PQ forms. And what we know is that this integration, with respect to these integrations, this round D and round D bar, both is differentials, right? You can easily see this equality. So this means, so because of this equality, this D bar plus UD is a kind of a goes to the homology group of these things. So you have a kind of pairing.
So there's a little bit here. So on the left of the screen, U is just a formal parameter. It seems to be a form on the right-hand side.
Oh, yeah. This U is a differential form. This U is formal parameter. I'm sorry. Yeah. Completely different things. Sorry. So this wedge product and integrations gives a kind of product, I mean, an inner product on this some cohomology group, and its value take this formal power series ring. And this is a version, something like just a compact Kähler manifold. And I think this kind of formulation came from another version, which is related to singularity theory in complex geometry, something called a half-infinite formulation of a Hodge theory. And in that case, this pairing is something much more non-trivial called higher residue pairings. That will come later on. So you have this story of this pairings and kind of family of boundary operators.
You're taking the pairing to be complex bilinear? And
yeah, this is complex bilinear, yes. No, not bar, yeah. So this is a story in a complex side of the story. In the complex side, you have this one parameter family of the cohomology groups, and you have this wedge product, and you get the pairings. And I didn't tell so much, but if X is a Calabi-Yau, then you have this N form, which is a holomorphic N form. globally. Then using this N form, you have this kind of things. PQ form can be identified. This is a tangent bundle, and it's a piece exterior product, and takes 0Q forms. This is N minus P, right? So you have N minus P exterior product of this tangent bundle, and you have Q form. So this guy is isomorphic to the PQ forms. And in usual mirror symmetry pictures, in place of this differential form of PQ type, we use this exterior power of the tangent bundle tensor with this 0Q forms. And then, this wedge product and these integrations together give some product structures. That is called Yukawa coupling. And that's the kind of main things which appears in this mirror symmetry in the complex side of the story. And in the simplex side of the story, this Yukawa coupling should correspond to something called a quantum cohomology. And in this complex side of the story, as you see that, for example, from this kind of things, the Hodge decomposition play kind of important roles. And mirror symmetry should be symmetry between complex and simplex geometries. So people somehow wonder what is this Hodge theory in this symplectic side. You can say that, of course, this cohomology group has a Hodge decompositions, but it's not so much a symplectic part of the stories, because Hodge decomposition is so much related to this integrability of the complex structures and the scalar properties. And there is a story called homological mirror symmetry. So homological mirror symmetry, you have a Hodge, in a complex side, you have a derived category of coherence sheaves. And then you have a complex manifold, and the derived category of coherence sheaf knows so much about this complex manifold. At least you know about Hodge theory. But then in a symplectic side, you have something called a cyclic infinity category, which I'll explain soon. So you have some categories. And then the questions is if you have just a cyclic infinity category, just something a bit more general than an associative ring, then you can say something about the Hodge theory. So that's something called, and this derived category of coherence sheaf should correspond to this infinity category, and that is homological mirror symmetry conjecture by Kontsevich. And this cyclic infinity category is cooked up from Lagrangian Floer theory. So this is a kind of more topological nature. This Hodge theory or and the coherence sheaf is more kind of local and a geometric object. And this is a kind of a simplex topology type object. So it's a kind of, but the difference is this guy, Lagrangian Floer theory, has a lot of global effect, which came from holomorphic curves. So you have some structures of associative ring or a bit more general cyclic infinity category. And from this kind of rings, what I want to explain today is you have a kind of some kind of a ring with some structures, and you want to cook some structures which looks very much similar to Hodge theory in a complex geometry. And something we expect is that we have this constructions of cyclic infinity category to some kind of a Hodge theory. Then what we get actually corresponds to Hodge theory in a complex side. So this is the reason of this parenthesis, because we just start from some infinity category or something which is not a complex manifold, but you cook up something which looks similar to Hodge theory. Okay, so this is something I explained. And this kind of story is not new to me. It's not new. And there is very many people who propose this kind of stories, especially the Kontsevich, Soberman, Katsarkov, Pantev, and Uru. And those people wrote a lot of papers about something called a non-commutative Hodge theory. That is the context of this kind of things. And also this story is a kind of Kyoji Saitoh and Takahashi has a lot of things about this. And they came from this complex singularity theory in complex geometries, and they look for the similar structures from category theory or algebras. So I want to explain this kind of category theory stories. So some part is very much algebraic. And then I will explain how it works in a particular case which appears in this geometric situations. So we start from differential graded algebra A. So it's an algebra which is associative algebra, not necessarily commutative, but we assume that it has a differential. So differential graded algebras. And there is something called a Hochschild homology. I don't want to explain the definition of Hochschild homology because this is a geometry festival. So I want to explain rather in geometric term. So I'll explain how it appears in geometry in the next slide. So you can just say that you have any associative algebra, you have some homology theory called Hochschild homology. And then on this Hochschild homology, there is some operator B, which is kind of invented by Alan Kohn when he studied this story of cyclic homology. You have degree 1 differentials. And using this Hochschild differentials and this B, one can cook up the very similar. So this is Hochschild, it's called Hochschild cochains. You take a tensor product, you have these operations. I didn't say, but you have this equality, and you have a very similar equality. That's very famous in this kind of B. B square is 0. This Hochschild differential square is 0, and B is 0. So you can pretend that this differentials in a Hochschild homology, this differential in Hochschild homology is like something like a d-bar operator in complex geometry. And this B, which I will explain, is something plays a role of this round D in a Kähler geometry. So you have these two operators, and using this, you have this Hochschild complex tensor with this formal power series. And then if you take its cohomology, then actually what you get is exactly the cyclic cohomology of your associative algebras. So I want to explain what are they. And in place of writing down algebraic definitions of Hochschild homology, I want to explain in some particular case, which is important both in our stories and also in this cyclic homology theory. Let us take A is a de Rham complex of some compact manifold. So it is commutative, but it's a kind of associative algebra, and you have a differentials and the wedge product. And then what is known here is that if you take this Hochschild homology of A, then it is a homology of free loop space of M. So if you think about the Hochschild homology, then you can just regard it as something like a loop space, homology of the loop space. And then you consider this operator B. It's a Hochschild complex, but just first take homology. So it's a map between homology of free loop space to homology of free loop space, and it's a map of degree 1. And it's defined in the following way. You have a P, say P is a cycle. L by M is a loop space. So in this talk, omega is a differential form, and L is a loop space. And they appear very frequently in this kind of talk, so it's a bit hard to distinguish them. But then if you have a P cycle, which goes to the loop space, and the loop space has a very famous S1 actions. I mean, you can reparameterize loop by S1s. So you rotate this cycle by this S1 actions. You have another cycle. So this is a degree plus, you have a degree K, you have a degree K plus 1 cycles. Then you have this degree 1 operator. This is B. And of course, this is a map between homology. So this just means that this kind of constructions goes to homology from chains. And you can easily see that if you repeat it twice, then this is 0, because if this is already a kind of S1 equivariant, then if you do it again, you have kind of too much parameters. So you get a 0 in homology. And actually, this operator B, I explained in geometric term, but you can define this in terms of Hochschild chains. There are algebraic formulas which you can define this operator B in a purely algebraic language. And it is actually a theorem that this cyclic homology is this S1 equivariant homology. But there is some delicate issues, which kind of completions you take and which kind of things you consider. There is some small difference, and it's not actually small. It might be very serious things, but today I ignore it and just pretend that the cyclic homology is S1 equivariant homology. So you have this S1 equivariant homology, and you have this Hochschild homology. But before going further, I want to point out one thing, that this example is not actually completely fit in our story. So if you consider this A in differential forms, as I said, that Hochschild homology is a homology of loop space, and cyclic homology of S1 equivalent homology of the loop space. But if you compare this S1 equivalent homology and H of Lm, then this is not a trivial. So I mean, in a case of this Hodge theory, we consider cohomology of, so in the case of Hodge theory, in the case of Hodge theory, it is. Yeah. So this cohomology of d bar plus ud is not so much a kind of complicated thing. It's just usual homology tensor of this formal power series ring. And so in our story, this homology group should be something related to Hochschild homology, and this is something called related to cyclic homology. So cyclic homology and Hochschild homology is something like just a tensor product. And this U, in this respect, regard to be somehow generator of cohomology group of CP infinity. You know, you have S1 equivalent homology, S1 equivalent cohomology or homology. So it is a module of a homology of CP infinity. You have a canonical generator C2, C1. This should be this U. And this kind of, so now I go back to this original, now I go back to this loop space situations. So this is not equal. So this is something like a homology, and this is something like a homology of d bar plus ud. And this is not a tensor product, because this one is isomorphism basically when this S1 actions of our space is trivial. I mean, if S1 action is trivial, then it's S1 equivalent cohomology is just a tensor product of the original homology times of this homology of CP infinity. But this S1 actions on a free loop space is highly non-trivial. So this equality is not correct in this particular case. And but there is an explanation. But then actually, in an actual case which I want to discuss, this equality should hold. And the reason that this is different from that case is the following. So if we consider something like A is a loop space of some compact manifold, this corresponds to the case that the symplectic manifold we study is a cotangent bundle of a compact manifold. So that is a kind of one of the most basic case of this symplectic topology. But the cotangent bundle is not compact. The reason is that this corresponds to this is the following. If you consider this cotangent bundles, and you consider Hamiltonian dynamics of unit cotangent bundles, and then Hamiltonian dynamics of unit cotangent bundle is so much related to the homology of the loop space, right? I mean, Hamiltonian dynamics of the unit cotangent bundle is basically the story of closed geodesics, and the closed geodesics correspond to homology group of the loop space. So Hamiltonian dynamics of this T star M is a homology of the loop space, and that is a non-compact case. I mean, because homology of the loop space is infinitely generated. But if you consider compact symplectic manifold, and you consider Hamiltonian dynamics on compact symplectic manifold, that is controlled by the homology of the symplectic manifold itself, not the loop space homology. So in that case, and I'll explain later, this Hochschild homology should be related to this homology of the ambient space in a compact case, but in the case of this cotangent bundle, it is related to the loop space. And as you see that this is non-compact, and Hodge theory on a non-compact space is very much different from the Hodge theory of compact space. So the situation is very much different, especially this kind of equality does not hold. And also there is another big difference. In a compact case, we can define pairings. So I think in the beginning, when I explain Hodge theory, I explained you integrate differential forms and you get a pairing of these cohomology theories. But in this non-compact case, there is no pairings. And one big reason is that there is no pairing is that this homological loop space is not finitely generated. So in a kind of Poincare duality or kind of good case, like there is pairings, you are supposed to have a finitely generated homology group, finite rank homology group. So this is non-compact case. It is important in symplectic topology, but if you want to discuss this case, you need a bit slightly change the stories. And I don't want to talk about it today. So now I want to go back to this story. So we consider this A, it's a differential graded algebras, and then you consider Hochschild chain, and you have two operators, Hochschild operator and this Korn's operator, which correspond to S1 actions. And then if you join them together using one parameter families, and you get this homology group. And what we want to do is just using from this kind of situations, we should cook up Hodge theory on the cyclic homology and Hochschild homology. And the main thing I want to express, so this is not what I proposed, and this is proposed by Konsevich Soberman and those people, and also Saitoh Takahashi and Pantev Uru and those people. And they talk a lot about this non-commutative Hodge theory, and that looks very interesting story, and that should be an important part of this mirror symmetry business. But what I want to explain is a it's very interesting, but it's a kind of a very difficult story to realize, and also to connect this non-commutative Hodge theory to some actual Hodge theory in complex geometry is another difficulties. But I want to explain today that there are cases that we can actually kind of construct this kind of structures. Not only this, but also some pairings, and also we can relate this kind of Hodge type structures to some Hodge structure which actually appears in complex geometry. So that's something I want to explain today. So I want to go back to the story a bit. So we consider symplectic manifold. I'm sorry, there is another error again. So L is a Lagrangian submanifold. So so loop space of L is L. It's not so good, but L is Lagrangian submanifold is too much usual. So I need to write L. This is the omega. This omega is loop space. No. Yeah, this is the differential form. Yeah. This is the differential form. So you take a loop space. You take a L Lagrangian submanifold. Then you take its differential form of a Lagrangian submanifold. They have a differential D and lambda. They give a kind of a cohomology ring, and the story of Lagrangian Floer theory is some kind of deforming this DGA to something which is called infinity algebras. So this FO is Ohta no. So what we did is somehow, if you know a bit about quantum cohomology, the story of quantum cohomology is you start from symplectic manifold, you consider its cohomology ring, but then you have this holomorphic spheres embedded in this symplectic manifold, and you use this holomorphic spheres to deform your ring structures to something which is called quantum cohomology. So that's the story of this quantum cohomology of compact symplectic manifold. But then we can do this very similar story in the case of Lagrangian submanifold. In case of Lagrangian submanifold, you consider not the so not a sphere, but we use this kind of pictures, Lagrangian submanifold, holomorphic disks. So in place of this kind of using holomorphic spheres, we consider holomorphic disks, and then you deform your de Rham complex to something which is called infinity algebra. And infinity algebra is a kind of similar to associative algebras, but your associativity is breakdown a bit, but it compensates by this higher MK. So you have an infinite series of operators, so that they give some nice relations. That's called infinity algebras. And here we start only one Lagrangian submanifold, but instead of using one Lagrangian submanifold, you can consider many Lagrangian submanifold. Then you get some category, and here, so the category. So here, so in the case you have just one object, it corresponds to this infinity algebras. You have several objects, they have morphisms, and the product of this infinity algebra is something like a composition of the morphisms. So that's how this infinity category is made. And one important point is this DGA, de Rham complex, is graded commutative. So it's still in a commutative world. But this infinity algebra is definitely non-commutative. So from here to here, we go from commutative world to non-commutative world. So this is, you have some non-commutative object. That is infinity category. However, I mean, if you have any associative algebras, you can still cook up this Hochschild homology. And there is a conjecture that you have a compact symplectic manifold, and you consider this category, you take many Lagrangian submanifolds, and you cook up something like associative algebras. You have additions and multiplications, and higher multiplications. And you take its Hochschild homology, then it should recover from original homology group of original symplectic manifold. I think this conjecture, it's first mentioned in Konsevich's talk at the International Congress Zurich. It's something like 20 years ago. And I think Paul Zeider made some more precise things. And now, in this 5 or 6 years, this gets more and more realistic. I think even for Kontsevich 20 years ago, it was scientific fictions, and he said scientific fictions. But now, not only for Kontsevich, for other people, this is a kind of problem which we can attack, and it is proved in various cases already. So this is a kind of realistic things. But we cannot expect that this holds in complete generality. But for example, if X is a projective algebraic variety, probably this is it is expected to hold. So you have a very large class of symplectic manifold, so that if we know this category, then its Hochschild homology is a homology of the space X. So the meaning of this is the following things. Somehow we want to forget everything about symplectic manifold itself, and we remember only this category. Kind of, I mean, the idea of string theory is something like in place of the target space, you forget the target space, and you have some other theory, which might be some kind of a field theory, and this field theory is some kind of a generalization of the space-time. And then what is the cohomology? Then this is an answer, right? Hochschild homology of that category is a cohomology of that space. But I don't want to go to that thing so much. I just want to stay more in mathematical things. But anyway, if we know this infinity category, then this homology group is something here. So now the natural thing is to do for this Hodge theory is in place of taking this Hochschild homology, we take this cyclic homology. But before going so, I want to explain a bit more about these conjectures. We can make this conjecture a bit more precise. We start from this Hochschild chain complex of this category. Then there is a map which is called open to closed map. Two is missing. Yeah, but so this infinity structure is something like an open string. Yeah, but this you have a boundary. This is called an open string. And then this map P star is called the open to closed map. And this is defined in complete generality. And the conjecture says that this particular map gives an isomorphism here. So you have a well-defined map between this Hochschild homology and the homology of ambient space. And the conjecture is that this is isomorphism in a very large class of the spaces. Okay, so now this is a one figure explanation of this map P star. So you have this Lagrangian submanifold L, and you have a P. P is a cycle on L. And I don't define Hochschild homology, but Hochschild homology is something like you can cook up with many tensor product of the homology group of L itself. You take a K tensor product of L, and you have a K tensor product of, say, singular chain complex of L's, and then you can just take this several product structures and the boundary operator together. That gives Hochschild homology. So element of Hochschild homology is a kind of cycles on your Lagrangian submanifold. Then you consider this. This circular cone is a holomorphic disk. You consider this holomorphic disk so that they hit these chains on the boundary. And then you consider Q. Q is a cycle on ambient space. Then you require that this intersects here. Then you count this kind of holomorphic disks. And you count this correctly, you get a map from Hochschild homology to the homology of the ambient space. That is this map P. And this is a one figure explanations. And actually, if you want to go more than one figure to write down the rigorous definitions, and this kind of thing is actually rather hard to define. You have to cook up many moduli spaces of holomorphic objects, and you want to make it you want to work out Fredholm theory, compactness, and you work out how to kind of orient it and how to perturb it so that everything is smooth. And the last piece is a kind of headache. And so for this kind of very sophisticated moduli space, use of moduli spaces, we build up some story called virtual fundamental chains, and we are working on this 18 years. But then in these years, in the Simon Centers, we are kind of doing some special semester so that to discuss the foundation of this virtual fundamental chain techniques. And kind of foundation is a kind of rather thick volume to write it up, and it's a kind of 1,000 pages of papers. So that's the reason that I don't want to explain more than one figures. And most of the formulas and most of the statement I wrote today is based on this kind of sophisticated virtual fundamental chain techniques. And if you see this kind of pictures, you can see many equalities about operators. You can see naively. Then most of those naive equality you can finally cook up in a rigorous ways, but it costs much. it costs a lot of papers, also a lot of times. So some of them is not yet written up by that particular reasons, and we need to kind of clean up everything about virtual things. So so we were going for a long time, and 1 or 2 years ago, we just decided to stop and to sit down to write up everything about foundations, and then maybe soon after we are ready to go back to go ahead. But anyway, so this is a kind of one figure definitions, and most of the operations or most of the statements are kind of proved by this kind of figures, and to make it figure to a rigorous proof is a kind of mathematical job. Okay, so now here is an example of some particular equality. So this is the P. It's a map from this Hochschild chain to the ambient chains. And then you have this B. Remember, B is a Cohen's operator. And in a geometric way, it's a kind of S1 actions. And one proposition is that this P composed by B is 0. And if you use this equality, then you can immediately see that B is a boundary. So this is Hochschild chain. Hochschild boundary is actually P and Hochschild boundary is 0 is easier. But this P composed with B is 0 is a bit more difficult, but they're correct. Then if you compose this, then we are taking cyclic homology is a cohomology with respect to B and this Hochschild boundary. So you can send this map from this Hochschild cyclic cohomology of this empty category to this S1 equivalent homology, because this U here plays a role of this S1 action generators. So this map. So this is the first corollary. So not only this P, we can cook up map from this cyclic cohomology to the S1 equivalent homology of the ambient space, and you can then there is this, in a situations of the cyclic and Hochschild homology, there is some exact sequence which is an origin of this operator B, and this many work by Alan Kohn is something like you have a Hochschild homology, and then the Hochschild homology, this is B, I think, right? And then there's the cyclic cohomology. You have this kind of exact sequence. And this exact sequence in the side of this X is just a Gisin sequence. And the Gisin sequence, you have S1 equivalent homology, and just a homology, they are related by this way. So then what we can do is just to compare this map with this Hochschild map and this H of X, and you do some algebraic machineries. It implies that if this P star is an isomorphism, then this one is also an isomorphism. And that's a kind of short proof of that cyclic homology of the empty category is isomorphic to the Hochschild homology tensor lambda U. The reason is that it is true in X itself, because X S1 action is trivial. So then you have a P is an isomorphism, so you can just prove this. It's a kind of cheap proof, but somehow the only non-trivial thing is to prove this. And I want to remark that this isomorphism is called the Hodge-to-de Rham degeneration conjecture. And that's, if you see this something which is related in Hodge theory, this is non-trivial. Because in a situation of Hodge theory, this is related to the fact that this Laplacian of D is equal to Laplacian of D bar and Laplacian of round D. So it's a kind of a very basic part of this Hodge theory. So this is highly non-trivial. And also, if I remind you that in the case of A is just a de Rham complex, then this is not correct. So this is not completely free. It is some important part of the story, and actually this is proved by I don't know this proof because this is purely algebraic and uses very difficult, sophisticated homological algebra. But Caledrin proved it, and in the case such something called smooth and compact, and this is a notion introduced by Kontsevich, and he introduced some smoothness of the AFET category, and. Yeah, and compact is related to this, cotangent boundary is non-compact. And smooth is related to the following things. If my understanding is correct, if you have a ring, then the ring is a regular ring if one don't leave, its homology dimension is finite, right? So you have a kind of finiteness of the homology group is related to the smoothness. I mean, the ring is regular means that corresponding algebraic variety is smooth. So the smoothness is something related to the finite degenerating of this homology group. And this smoothness is in the sense that this A has a kind of finite dimensional homology groups. And so in a case of loop space, it's not finite dimensional. Loop space homology is infinite. So they are neither smooth nor compact. But in a case smooth or compact, it is this kind of thing is correct. And so that should be the case when you have with this infinity category associated to compact symplectic manifold. So in that case, you have this Hodge-to-de Rham degenerations. I mean, if you consider non-compact space like affine varieties, the Hodge theory, you have some more sophisticated Hodge theory, but it's not such simple. Okay, so now this is about this. And then there is a pairing. There is a story of pairings. So first of all, we want to cook up these pairings on this cyclic cohomology, on this Hochschild homology. And to define these pairings, the main thing we use is a Poincare duality on your Lagrangian submanifold. So you have this Rham complex of a Lagrangian submanifold. We use wedge, and we use this. We use wedge, but something we don't. We use wedge and D, but something we didn't use is integrations on L, not on X. So L is a compact Lagrangian submanifold, so you can integrate differential forms. So it gives this Poincare duality. And another thing we use is the Rham complex has a unit, 1. So we use 1 and no, not 1. Yeah. We use this Poincare duality to cook up these pairings. That's a bit complicated formula. So I first show figures. So this is one figure definitions. So this is a pairing between element of Hochschild homology and Hochschild homology. So you take P0, Pn. P0 to Pn is a cycle on your Lagrangian submanifold. And Q0 to Qm is another cycles on your Lagrangian submanifold. Then we consider this figure. So this yellow one is a holomorphic disk. You have a holomorphic disk which goes to this, whose boundary goes to Lagrangian submanifold. And you have another holomorphic disk, this pink or orange. And then we require that this point and this point, they glued. So you have some strange figure from this Lagrangian submanifold, from this holomorphic disks. And you have this n plus 1 chains, so you require that this n plus 1 chains hit this outer circle somewhere. And you have n plus 1 chains, and you require this n plus 1 chains hit somewhere on this inward boundary. So you have some strange configurations of holomorphic disks, and you count such holomorphic disks with some weight. And we consider only the case of dimension is 0. So you get some number. And then this number is this pairings. And you can, so this is a kind of geometric meanings. And this number, you can rewrite it to the, in a language of this infinity algebra and Poincare duality pairing of your Lagrangian submanifold. So in a simplest case, it is this formulas. But I don't want to explain definition. But it's a kind of state sum over this basis and using Poincare duality. So this is the pairings on this Hochschild chains. And so something a bit new here is we consider this pairings, which we call residue pairing. So I forgot it. This pairing is, in the case of we have only one element AB here is in our papers, but with Mohamed Abouzaid, we generalize it to this Hochschild chains. So now we have this equality. So you remember that this equality, right? You have this wedge product and integrations, and they are compatible both to the bar operator and D operator. That gives this pairings or integrations of a complex manifold, Kähler manifold. So we want to imitate this story in this non-commutative world. Then we define these pairings, which looks very strange, but it's a reasonable pairing. One big reason is that we can prove, for example, this kind of thing. So this first one just means that this is a kind of compatible with the usual boundary of Hochschild homology. And the second one is this is compatible with this Con's operator, S1 actions. So these two, you can immediately see that this is very much similar to this formulas. So using these two formulas, you can immediately find that this one extends to the pairings on the cyclic homology of our infinity category of the Lagrangian Floer theory to this lambda u. I'm sorry, this lambda is something called a Novikov ring. That corresponds to the fact we have when we count this kind of configurations, actually there are infinitely many of such configurations. But if we consider some area of the holomorphic disks, it is only finitely many. So you take some formal power series with just using this areas. That's a Novikov ring. So that's this lambda. So you have some ring lambda in place of complex numbers, but you have this very similar story of this integrations here, and you get this pairings. So this is something which we believe to be analog of higher residue pairings in complex geometry. So, and also then if we consider this map from Hochschild homology to H, then we can prove that this this residue pairing, which I just defined, is exactly become a Poincare duality pairings on X. So if you compare this kind of non-commutative world of this infinity category, then using the structures of infinity category, you can define the pairings. And you have a relation from this infinity category to the homology of the ambient space. But then if you go from here to here, then in a usual geometric world of this compact symplectic manifold, these pairings I just defined is exactly equal to the Poincare duality pairings. So this means that if we forgot everything about X, but you have only Lagrangian submanifold and how they interact, then you can recover this H of X together with this Poincare duality pairings. And also there are cup product kind of things. And if you include this cyclic, then this is also, so here this pairing is just S1 equivalent homology goes to this S1 equivalent homology point. So you have this natural pairing. So you can recover S1 equivalent homology of X in terms of this infinity category. So now this is a kind of general story. So as far as we have this enough many Lagrangian submanifold so that its Hochschild homology knows the homology of the ambient space, then you can recover the ambient space homology and Poincare duality and also cup product and quantum cup product in terms of this infinity category. And then I want to explain how this stories which I explained for this infinity category is related to this complex part of the stories. And this is a bit slightly more general case of this, slightly more kind of modified case of Hodge theory in complex geometry. That's a kind of Hodge theory of singularity theory. And so in the Hodge theory of singularity theory, I think this F should be W, I'm sorry. You have one holomorphic functions on n-dimensional complex vector space, for example, which has a 0 as an isolated singularity. So that's a kind of story. That's a kind of story in the singularity theory. Then we consider holomorphic differential forms on these complex numbers. Then we modify the story a bit. So here in complex geometry, you have a d-bar operator. So compact complex scalar manifold, you have a d-bar operator and you have a d operators. But then here you have a complex manifold. So this F and W is the same thing. I'm sorry. So you have this complex manifold. You have holomorphic functions W. Then we consider the differential forms. Then in place of this d-bar operator, we slightly perturb it. D-bar, you take d-bar, and then you take this wedge of dw. This is one form. And then the d is just the same thing. So we just slightly modify this because this is a complex number. So without this w, it's just a kind of Hodge theory, just trivial. But then you have functions whose critical point is only 0. Singular point is 0. Then you do this perturbation. You can see very similar story as in the usual Hodge theory. So then we consider this cohomology. So we have these two operators which play something similar role as d bar and d. We consider this homology group. Then so in a usual compact case, you get this cohomology group tensor. And this may be C, yeah, sorry. Complex group with formal parameter. But then here, if you include this, then you get something called the Jacobian ring of W, tensored with this formal power series. So let me remind, what is Jacobian ring? So W is a function on complex numbers. Then you consider all homomorphic functions, and you divide it by the ideals, which is designated by the differentials of these W's. And in the case when the W has isolated singularity, this is a finite dimensional ring. For example, in the case W is just the most functions, this is just a rank 1 ring, isolated on this critical point. And here's bigger, this is a bit big. So this is called a Jacobian ring. And this Jacobian ring controls the deformation of the singularity theory. But then, you take this wedge of d bars, they have a kind of, then you take the cohomology of these operators, wedge dw. That is something similar to Koszul complex, and then its cohomology is actually this Jacobian ring. So if you kind of study this cohomology, then it is Jacobian ring with this one parameter u. So this is an analog of Hodge theory in singularity theory, and this formulation is a kind of invented by Kyoji Saitoh many years ago. Okay, so now and then something so there are something important is this pairings. So in a complex geometry, you can easily take this wedge product and integrate. And in this singularity theory, it's a bit more subtle because this is non-compact. But there is a kind of notion of pairings in this Jacobian ring that's called residue pairings. And that's something related to integrate differential forms on some vanishing cycles or some generators on this homology group. So you have this some notion of integrations on this singularity theory. And one important part of this Saitoh's theory is generalize this usual residue pairing to higher residue pairings. So the residue pairing takes about in complex numbers, but they have a formal power series. So you have a kind of infinitely many kind of lift of the pairings, infinitely many series of pairings. That's called higher residue pairings. And that's become more non-trivial than usual integrals. And how this higher residue, to understand this higher residue pairings and something called primitive form is a kind of main part of this story of singularity theory. And those stories appear as a kind of mirror to usual Frobenius manifold structure of quantum cohomology. And this Frobenius manifold structure is due to Dubrovin. And this Saitoh's formulations and this Dubrovin's formulation is expected to be coincide. That gives a kind of mirror symmetry. And so now we have this Jacobian ring, and we have this higher residue pairings. And then what I want to explain in the remaining minutes is just if you consider this story about singularity theory, then if you want to do this in a kind of symplectic manifold case, then if you consider Toric manifold and some particular symplectic manifold, then you will see almost the same structures here appearing in this Lagrangian Floer theory settings. So that's something I want to explain. So I want to consider Toric symplectic manifold. It means that you have a symplectic manifold X together with n-dimensional. So this is a complex n-dimensional manifold, and it's a Keller, so it's a symplectic structures. And you assume that you have a torus actions on it, which preserves symplectic structures and which has a moment map. This is a moment map. So you have a map from this X to Euclidean space. I'm sorry, this is Rn. Sorry, this is Rn. You have a polygon. You have a convex polygon. That's the image moment map. And then if you have any point C, I'm sorry, C is a point of P. If you have any point of C, the inverse image, it is a tori. It's the interior of the moment polytope. You have a Lagrangian tori, and that is the orbit of this torus actions. So for any point on this moment polytope, you get a tori, Lagrangian tori. So now what I want to do is that we consider this Lagrangian tori, which is the orbit of this Then what we did in this Lagrangian Floer theory is we start from this differential graded algebra for this tori. So this is something related to this loop space of the tori. Then Lagrangian Floer theory is something like a deform this de Rham complex of the torus to some infinite algebras. So first we consider this. So before deformations, before including anything about simplex geometry, anything about holomorphic disk, we just consider de Rham complex of tori. So what is de Rham complex of tori? And we want to consider Hochschild homology of the de Rham complex of the tori's. You don't need to know the definition of Hochschild homology. All you need to know is that Hochschild homology of the de Rham complex is a homology of the free loop space. So what is the free loop homology of the free loop space of tori? And this is easy, right? Free loop space. So this is a connected component. It is parameterized by g to the power n. In each element of pi 1, you have a free loop space. And the connected component of free loop space is homotopy equivalent to torus itself. Right? You have any homotopy class, then you have a unique, you have a closed geodesics, which is a kind of parameterized by its origins. So this is a kind of infinitely many direct sum of homology of tori. So before perturbations, I want to regard this one is a kind of sections of K0 forms on n-dimensional complex vector spaces. How we can do it? So this homology group of torus is an exterior algebra with n generator. Right? N-dimensional tori, it's a kind of exterior algebra with n generators. So it is here. You have a exterior product of n generators. Then you have this z of n, which is pi 1 of your tori. So then you use Fourier transformations. So you have a kind of element. So a gamma is actually here, but you have a kind of formal power series of n of gamma. Gamma is n parameter. Then you can just associate it to this Fourier series. A gamma x1, gamma 1, n x gamma n. So you have this Fourier series. And then in this way, you may regard that this element to functions on complex vector spaces. So by this, in this way, you can regard this Hochschild homology of the Rham complex, that is the homology of free loop space, as a sections of this N0, K0 form on n-dimensional complex vector space. So this is before you put anything about holomorphic disks. You get this. So this looks already similar to something which appears on this singularity theory. Then what we do is following. We start with this Rham complex. So there is no quantum effect, nothing from holomorphic curve. But then if you use this holomorphic disk, which bounds your tori, then your DGA will become to infinity algebras. We have some effect of holomorphic disks. And we can explicitly calculate this effect. I don't want to calculate it, but then it's following things. We start from this Hochschild complex, then you end up with, we start with Hochschild homology of the Rham complex, and you end up with the Hochschild complex of this infinity algebras. There is a spectral sequence which goes from here to here. And the boundary of the spectral sequence is actually wedge of dw, plus something extra. But at least the leading term is operation which takes wedge of this d of this some function w. And this w is generating functions of counting holomorphic disks.
There was a subscript C with compact supports.
No, C is a point in a moment polytope. So TC is a kind of parameterized by this point. So we have a function on H1 of Tm, and this W of B is defined by these formulas. You have this flat thing is L. You consider this U is a holomorphic disks. So you count these holomorphic disks with weight. You have a boundary here, right? You have S1. And then you have B. B is a H1. So you integrate this B on these boundaries. And you take from formal parameter. You take this strange sums. You get some functions. And this function is called Landau-Ginzburg superpotentials in string theory. And we found it as a kind of a version of obstruction theory of Lagrangian Floer theory. So we take these particular functions. And then we calculate Floer's differential, Floer boundary. It means that the deformation of your cup product with using holomorphic disks. And you end up with this operation is just to take a wedge with d of these particular functions. So now, right? Oh. Now the story is following, right? And also you have another thing. It's B. So B is what? So B is a Collins operator, and B in this case is a S1 action. So this one you identify with the homology of free loop space, and then homology of free loop space of S1. You have this S1 actions on the loop space. And then you can easily calculate what this B is in this particular case. It's a kind of homology of the loop space. So you see what it is. And then if you calculate it, then you end up that this B is just around D. If you identify this one with this Cn with this differential forms, it's just around D. So This is actually very easy calculations. Nothing about the moduli space. It's direct thing, homology things and loop space. So now finally we end up with the following things, right? I mean, if you consider this B, it is it is around D, and you consider this difference between usual homology and Floer homology, then it is a kind of leading term is a wedge of D of W. And then you go back to the complex story, you have around D and D bar plus DW. This is a kind of Hodge theory type thing in a singularity theory. And if you see these toric situations, you get exactly the same thing. You have around D and wedge of D bar, DB. And what we know is that then this Hochschild homology is a Jacobian ring on this of this particular function W, which is the random Ginzburg potentials. And then you can just kind of parallelly compare the stories. And something I explained before is that we can cook up pairing here, and which lifts to the cyclic homology. And in this there is a kind of deep pairings, the Kyoji Saitoh called higher residue pairings, and it coincides up to higher orders here. So it's something like not exactly, but probably this higher means that this is not exactly equal to this, but kind of some correction, quantum corrections. So we in this particular settings on this toric manifold and under Ginzburg models, you have kind of very much a parallel stories, kind of Hodge theory coincides. Yeah, and also in this case we can prove that this Jacobian ring. You take all the C. This is I think product, not coproduct. Then it is a kind of isomorphic to the ambient cohomology. So in this case, and then you have this H of X. You have the story of this Robin story of quantum cohomology. So you get put back, so you get the story here, and the story, the kind of story on this of this Hodge theory type things from this non-commutative categories, and then they should coincide with this singularity theory of the stories. So that's I mean, so the stories are at least closing, close to kind of complete in this particular cases. Yeah, that's a summary. So using Floer homology and its affinity structures, we can find some kinds of structures, some kind of structure which is similar to Hodge theory in Hochschild and cyclic homology, and especially if an open closed mark is an isomorphism, it has a non-degenerate pairings, which should be some kind of higher residue pairings, and conservative Soberman's Hochschild Rham degeneration can be proved geometrically in that particular case, and in the particular case of toric manifold, that the whole structure match with Kyoji Saitoh theory of singularity. Okay, so thank you very much.
Any questions?
Claude. So could you explain how one chooses the Landau-Ginzburg potential W in terms, how is that related to the choice of toric manifold?
I mean, it's this. Yeah. So it's a kind of generating functions by counting holomorphic disks.
I see. And the toric structure is crucial for what reason?
I mean, for the toric structures, one particular way to use toric structure is the Lagrangian Floer theory is rather delicate things. You have some kind of, you need some unobstructedness. And we use this Tn actions to prove all the Tn orbit is obstructed in a sense. So.
But in principle, it's the key thing is that these give you a lot of Lagrangian submanifolds, and in principle you could.
A lot of unobstructed Lagrangian submanifold. So not only Lagrangian submanifold, but the Floer homology is very defined. But the full story should work, but somehow, and also we use a lot of toric structures to calculate many of these structures. And for example, if you want to prove that this Hochschild homology is isomorphic to the ambient homology, you need something. You have to find a lot of Lagrangian submanifold, which has a lot of non-trivial Floer homology to detect all the ambient homology. So that's non-trivial.
Any other questions? Let's thank the speaker again.